All right, welcome to this explainer where we are going to absolutely master the AQA required practical on electrical resistance. If you're looking to nail those exam questions on circuits, this is for you.
So here's our game plan. We'll kick things off with what resistance actually is. Then we'll build the circuit, run a couple of key investigations, and finish up by digging into the data and how to avoid those common mistakes. Let's get to it.
Okay, first things first. Before we can even think about measuring resistance, we need to be totally clear on what it is we're actually dealing with.
So you got to ask the big question, right? We know that electricity is just this flow of charge, but what gets in its way? What's stopping it from just flowing perfectly?
And the answer, of course, is resistance. This is a definition you've just got to remember. Think of it like electrical friction. It's the opposition that every single component puts up against that current. So the higher the resistance, the tougher it is for that charge to get through.
And this is where it all clicks into place with this absolutely crucial equation, V equals I times R. The potential difference, that's your voltage, it's the push. The current is the flow, and resistance is the opposition trying to stop it. This little formula is the heart of this entire practical.
Okay, so how do we actually go about building the circuit? To investigate V, I, and R, you've got to put your equipment together correctly. Getting this part right is everything. Otherwise, your results will be meaningless.
Think of this as your essential toolkit. You've got the battery providing the push, the ammeter, which measures the current flowing through a point in the circuit, and the voltmeter, which measures the potential difference across a component. Really understanding the job of each one is the key.
And here is the bit you absolutely have to get right. The ammeter has to be in the main loop of the circuit. That's what we call in series, so it can measure all the current flowing through. But the voltmeter, that's different. It goes in parallel, so it's bridging across the component you're testing. Seriously, burn this into your brain. Ammeter in series, voltmeter in parallel. It's a classic exam question for a reason.
Right, on to our first proper investigation. We're going to use the circuit we've just built to answer a really specific question. If we make a wire longer, does it get harder for electricity to flow through it, or easier?
Now, to do this like a real scientist and get top marks, you have to get your head around variables. The independent variable is the one you choose to change. In this case, that's the length of our wire. The dependent variable is what you measure to see the effect, which is the resistance. And the control variables? Well, they're everything else you have to keep exactly the same to make sure it's a fair test.
Okay, let's switch gears for our second investigation. This time, instead of just one wire, what happens when we start combining multiple resistors? We're going to look at the two main ways you can connect them, one after another, which is series, or side by side, which is parallel. In a series circuit, it's pretty straightforward. The current has to fight its way through every resistor one by one, so the total resistance just adds up. Simple. But parallel is where it gets a little weird. You're actually opening up more paths for the current to take. It's like opening more checkout lanes at a busy supermarket. The overall flow gets easier. So, and this is the bit that seems strange at first, adding a resistor in parallel actually makes the total resistance go down.
Right, so you've done the hard work, you've got your readings, but now what? A table full of numbers doesn't mean much on its own. Let's look at how we turn those results into a proper, solid conclusion.
Just take a look at this sample data for our wire investigation. See how we've calculated the resistance for each length? Now, can you spot the pattern? Look, as the length doubles from 20 to 40 centimeters, what happens to the resistance? It pretty much doubles too. That's a massive clue right there. A table is good, but you know what's even better for spotting a pattern? A graph. So if we were to plot resistance on one axis and length on the other, what kind of shape do you think we'd see? And more importantly, what would that shape tell us?
Well, that graph should be a perfect straight line right through the origin. And that proves it. Resistance is directly proportional to length. A component that behaves like this is called an ohmic conductor. And this definition is an absolute must-know for your exam.
All right, we are on the home stretch. Let's talk about the sneaky things that can go wrong. Being able to talk about errors scientifically is where you can pick up some serious marks in an exam, because it shows you really understand what you were doing.
These are the big three you need to know about. A zero error is simple. Your meter just isn't starting from zero. Parallax error happens when you read the scale from an angle instead of looking at it dead on. But the heating effect is the most subtle one. As current flows, the wire gets hotter, and that actually changes its resistance. A top tip to reduce this is to use a really low current, or even better, switch the circuit off between your readings. And these errors aren't all the same. They actually fall into two main camps. A systematic error, like that zero error, is going to push all your results off in the same direction. But a random error, like parallax error, just creates unpredictable scatter in your data. Knowing the difference is a really high-level skill.
So after all that, what are the absolute key takeaways? Here's your 5-point checklist for this practical. Get these facts locked in, remember the method we talked about, and you'll be set for any question they throw at you. Good luck.